56 million years ago, crocodiles basked beneath palm trees at the North Pole. Earth's hottest mystery, when the planet warmed by 8 degrees Celsius in just 20,000 years, turned the Arctic into a subtropical haven, unleashed over 2,000 gigatons of carbon, and acidified the oceans on a scale our species has never witnessed. The clues to this climate chaos are hidden in ancient mud and strange fossils, but the true cause remains fiercely contested. How did a frozen world tip overnight? And what warning does this shocking chapter hold for our future? The answers start with a strange spike in the carbon record that stunned the scientific world. Deep beneath the ocean floor, a thin tube of mud tells a story no one expected. In the early 1990s, teams at the core labs in Bremen and Woods Hole began slicing open sediment cylinders, some the width of a soda can, each packed with millions of years of layered history. They shaved off thin wafers, ran them through mass spectrometers, and plotted the carbon isotope values on long scrolls of printer paper. Most of the time, the numbers drifted gently up and down. But then, in a core from the Pacific, the graph nosedived. The isotope ratio, delta 13C, plunged by more than 3 parts per thousand almost overnight, at least in geological terms. No known volcanic event or asteroid strike matched this fingerprint. For James Zakos, then a young geochemist, it was like watching the EKG of a heart attack. He checked the calibration, ran the analysis again, and called in colleagues. The same spike appeared in North Atlantic and Southern Ocean cores. Within months, labs from New Jersey to Denmark were reporting the same signature, a sharp global drop in heavy carbon, all at the same horizon. The magnitude was staggering. More than 2,000 gigatons of carbon had to be injected into the atmosphere and oceans to pull the global isotope curve so far, so fast. The numbers forced a new question. What could release that much carbon that quickly? Zakos and his team started calculating, scribbling mass balance equations on lab whiteboards late into the night. The data didn't just break the rules, it rewrote them. Now, the hunt was on to trace the source and understand the consequences of the greatest carbon spike in Earth's last 100 million years. In the world of ancient climate, numbers can be more shocking than fossils. The PETM delivered a carbon surge so massive it's hard to scale. Over 20,000 years, barely a blink for geology, more than 2,000 gigatons of carbon flooded the atmosphere and oceans. That's enough to double the air's carbon dioxide, rivaling the total carbon stored in all of today's known fossil fuel reserves. James Zakos and his team calculated the math on lab whiteboards, cross-checking sediment cores from 3 oceans. The temperature curve didn't just climb, it shot up. Global averages spiked by 8 degrees Celsius. For context, the difference between the last ice age and today is only about 4 to 5 degrees. Here, Earth leapt twice that gap and did it in a fraction of the time. Proxy records, oxygen isotopes from foraminifera, fossil leaf margins, even the chemistry of ancient soils, all trace the same story: a planet in overdrive. Deep-time climate models forced by the carbon input show subtropical conditions invading the poles and tropical zones expanding across continents. The numbers leave no room for doubt. This was the biggest, fastest natural carbon release in the last 100 million years, and its fingerprints are written in every layer of mud and chalk from New Jersey to Denmark. The question wasn't just how it happened, but what kind of world it created. The consequences of this carbon shockwave would soon be visible in every ecosystem on Earth. On Ellesmere Island, a place now locked in darkness half the year, paleontologists crouch beside slabs of sandstone. They chip away mudstone to reveal palm fronds pressed flat as paper, their outlines sharp and unmistakable. Nearby, a row of crocodile vertebrae, unmistakably reptilian, rests where a river once meandered through a steaming forest. The Arctic, at 78 degrees north, was no icy wasteland. Instead, it was a swampy paradise, dense with broad-leaved trees, ferns, and the occasional dragonfly the size of a sparrow. Appy Slies, who specializes in ancient Arctic microfossils, describes pollen samples from these rocks. The slides are packed with warmth-loving species, more like Florida than the modern Arctic Circle. Fossil wood lacks growth rings, a giveaway that winters stayed warm and dark, never freezing. Even in Antarctica, palm pollen and turtle shells turn up in the siltstones of Seymour Island. The poles, once thought to be the planet's deep freeze, supported not just crocodiles and turtles, but mammals that adapted to the heat. Some so small, they've been called prehistoric hobbits. These discoveries force a new image of the ancient Earth, a world where the boundaries of the tropics stretched all the way to the top and bottom of the globe. Shells that once blanketed the sea floor began to vanish almost as soon as the carbon spike hit. Foraminifera, tiny plankton with chalky shells, left behind a sudden gap in the fossil record, as if entire populations dissolved in place. Geochemists in Bremen and Woods Hole noticed the change under the microscope. Where elegant spirals once filled every field of view, now there were only ghostly outlines and scattered fragments. Ocean acidity had surged, dropping pH enough to eat away at calcium carbonate. This wasn't a gentle shift. In some cores, more than half of deep-sea foraminifera species disappeared within a few thousand years. The surface waters suffered too. Even the shallow seas, buffered by rivers and weathering, turned corrosive. At the same time, rainfall patterns spun out of control. Hydrogen isotopes in ancient leaf waxes and spikes of kaolinite clay in sediments reveal a world of relentless downpours. The poles, once dry and cold, became sodden, muddy floodplains, sprawling deltas, and thick mats of organic debris washed into the sea. Climate models and core data agree. Polar rainfall likely doubled, maybe even tripled. The carbon shock didn't just warm the planet, it pushed every ecosystem, from plankton to polar forests to the edge. Two suspects quickly rose to the top of the PETM mystery board: volcanic carbon dioxide and methane hydrates locked in ocean sediments. The first line of evidence points straight to the North Atlantic Igneous Province, or NAIP, a colossal volcanic system that raged as Greenland and Europe split apart. Layers of clay in Denmark and the North Sea record sudden spikes in mercury, a chemical fingerprint of volcanic eruptions. At precisely the same depth, osmium isotopes in marine mud swing toward mantle values, matching the timing of the PETM's carbon isotope crash. Geochemists like Lee Kump argue these signals are hard to fake. Volcanism left direct traces in both metal and isotope records. But the story doesn't end there. Gerald Dickens and his team focus on the fingerprint of the carbon itself. The Delta 13 C drop is so extreme, down to -60 per mil in some compounds, that only a burst of methane with its ultralight isotope signature fits the bill. Methane hydrates, frozen in seafloor mud, could thaw and bubble up once the ocean warms, adding fuel to the fire. Computer models show that neither volcanoes nor methane alone can explain all the data. Instead, the best fit comes from both: volcanic sills igniting buried organics, releasing CO2, and triggering a cascade of methane release. Each clue brings scientists closer, but the debate over which source mattered most is far from settled. Not every scientist is convinced that volcanoes and methane tell the whole story. Mark Pagani, a Yale geochemist with a reputation for chasing lost patterns in ancient mud, started looking for a deeper clock. He mapped out paleoclimate records against Earth's orbital cycles, precession and eccentricity, the slow wobbles and stretches in our planet's path around the Sun. The timing was uncanny. The PETM's carbon spike lines up with a precession maximum nested inside an eccentricity high, a rare orbital combination that boosts summer sunlight at the poles. Pagani's datasets show these cycles repeat every 100,000 and 21,000 years, like a metronome for climate chaos. Still, orbits alone can't inject thousands of gigatons of carbon. Some researchers point to thawing permafrost, ancient peat frozen at the poles, suddenly melting as summers grew hotter. Carbon modelling hints that Arctic soils could have coughed up extra greenhouse gases, but not enough to match the scale seen in the cores. There's even a fringe theory about a comet impact, but the sediment layers lack the telltale iridium or shocked quartz. Every new dataset adds another layer of complexity, and the PETM's true trigger remains just out of reach. A puzzle with too many moving parts and no single smoking gun. 56 million years ago, the Arctic saw crocodiles and palm trees thrive as global temperatures soared by 8 degrees Celsius in just 20,000 years. A change traced in deep sea cores by James Zakos and colleagues. Fossils from Ellesmere Island and Antarctica confirm subtropical life at the poles, while ocean sediments reveal catastrophic acidification and mass carbon release over 2,000 gigatons. The exact trigger for the Paleocene-Eocene Thermal Maximum remains debated. Volcanic eruptions, methane hydrates, and orbital cycles all leave their mark in the geological record, but no single cause fully explains the event. Today, evidence shows Earth's climate can shift abruptly when carbon levels rise, an insight echoed in the modern rise of atmospheric CO2. The PETM stands as a stark example from Earth's archives. Rapid carbon release reshapes the planet, with consequences that scientists are still working to fully unravel.